Coming up next on Arizona Horizon, it's time for another update of the latest science news with renowned ASU physicist Lawrence Krauss. Science Matters with Lawrence Krauss next on Arizona Horizon.
Arizona Horizon is made possible by contributions from the Friends of 8, members of your Arizona PBS station. Thank you.
Good evening and welcome to Arizona Horizon. I'm Ted Simons. Every month, ASU physicist and best-selling science writer Lawrence Krauss joins us to discuss the latest in science news, which tonight includes details of a recent spacecraft landing on a comet. And here now is our good friend, Lawrence Krauss. How are you?
It's great to be back here in the holiday season.
All right, well, it's good to have you back on the. Hey, have you seen this movie Interstellar? This movie Interstellar about all the science, all this great science stuff.
Let's not waste valuable time talking about nonsense. It was one of the worst movies ever made.
Oh, how come?
There was nothing good about it. The science was miserable, the plot was stupid, and it was derivative. Other than that, though, if you had some good popcorn and maybe felt like a rest, it's a good place to be, because it's far too long. As I tweeted, three hours can seem like 23 years. Oops, gave it away.
So, but these people going through a wormhole to come back and save the Earth and all.
What? It saved the Earth from what? And how did they save the Earth? And with a formula? And how was the Earth dying? With some ridiculous mold that was somehow eating up the oxygen in one generation that it took 2 billion years to produce? It was just plain silly.
Last point on this, though, this Kip Thorne, a very renowned, another
and a friend of mine, and a very good physicist, and I feel badly that his name is associated with the movie. He had an idea early on about how to do a movie about wormholes, and real stuff, and then it got turned by Hollywood into garbage. Well, it's this process where they churn things and they produce garbage in the end.
All right. Well, at least you're not wishy-washy about that.
Yeah,
Let's talk about reality.
No,
though.
In fact, the New York Times asked me to see it, and I basically told them that they owed me 3 hours of my life. And they wanted me to comment on it. And anyway, sorry, go on. Let's talk about real good stuff.
Newspapers don't ask me to go see film. They asked you to go see a film on their dime?
Yeah, but they never paid me for it.
Okay. All right. Let's get to reality here. The Rosetta mission. Okay, spacecraft finds a comet, lands a little lander on the comet. Why this particular comet?
Because it was accessible, I think. But I mean, we're going to talk about a lot of neat stuff today. And I want to start with the heavens before we move to the earth, it being, Christmas season and all, and stars. And we're going to go to stars, and we're going to talk about the real wisdom we get from stars. And the Rosetta mission is an amazing mission. And everyone, I'm sure, has heard of it because it's gotten a lot of press. It was not just finding the comet. We knew the comet was there, but we had to plan a mission to get to it. To get up to speeds, I think it's 40,000 miles per hour or something like that it's traveling. And the spacecraft, in order to get there, took 10 years because its own fuel wouldn't have done it. It had to get slingshotted around planets to get there and then try and land a little lander on this thing where, in fact, the lander was let fall because it couldn't be directed. And what happened is used the gravity of this small comet, which is 2.5 miles across, to gently pull it down. The problem, of course, which is an amazing engineering problem, the fact that it got so close to working is amazing. The lander actually fell down about the speed at which you'd walk, because that's how gentle the gravity is. And it was supposed to then have some rockets that would hold it to the comet and some harpoons. And unfortunately, those didn't work. So the comet bounced. And when you bounce and there's no gravity, it bounced about a half a mile up in the air, came down, bounced again, and unfortunately landed in a place with some shadows because right up against a cliff, basically, on this comet. But the reason we want to land on a comet, and so therefore it wasn't going to get as much sunlight as it would otherwise, which power the solar cells. So it worked for about 60 hours, and it's not clear if there'll be enough light for it to really function after that.
It's kind of in hibernation right now.
It's in hibernation, which means it's not dead. It's just hibernating. In fact, hibernation was big on this spacecraft. This is a 10-year mission, and in order for the spacecraft to actually function when it needed to, it went into hibernation for 2.5 years on its trip to the comet. And in fact, only last January was taken out of hibernation, and that was a really knuckle-biting moment because you didn't know if it would come out of hibernation after 2.5 years, and it did. So most aspects of this mission has been successful. The fact that you could actually steer and parallel a comet traveling 40,000 miles an hour and then let a little lander go. It's just amazing. And of course, it could have worked better if it had worked all the way, but we've already learned an incredible amount. The reason we want to land on a comet is that the comets are primordial material from the beginning of the solar system, 4.5 billion year old stuff, balls of ice and dust, and they, among other things, brought material to the Earth. So this is the primordial material, some of which may be seeds for life. And so we wanted to find out what's on the comet, and already they found out it was much harder. They thought it would be a much softer surface. But some other interesting things have been two things, one of which we've talked about. The spacecraft itself, which is paralleling the comet, has looked at gas that's being emitted by the comet, looking at water. And as you may remember from an earlier discussion, we wonder where most of the water on Earth came from.
Yes.
And there's a big debate about whether it came from rocks or from comets. And the problem is most comets have a different ratio of the two isotopes of hydrogen, deuterium to hydrogen. In our oceans, there's a little bit of deuterium, which is why we can make heavy water. It's a heavy version of hydrogen. There's 1 part in 100,000 or so. When we look at comets, many of them have a different abundance. So if they have a different abundance of heavy water to light water, how could they have transported the water to Earth? One recent comet we found actually had the same abundance as Earth. So one of the things we want to know by going on this is, does this comet have the same abundance? And in fact, it turns out to be different. So it again tilts the scales in favor of the idea that maybe the water on Earth was primordial. It was stored in the rocks that created the Earth, deep inside the Earth, and couldn't evaporate. Or maybe it was brought by asteroids, rocky things instead of ice. Another thing we've learned is that they're organic materials. The Philae lander landed long enough to be able to sniff out carbon and hydrogen, suggesting organic compounds. One of the big questions we have is, was life on Earth seeded by comets? Not by little microbes, but were the elements, the molecules that make up you and I, the basic organic constituents that later became life, did they come from comets? And indeed, now we know that at least it's possible there are organic materials on this comet. So we've already learned an incredible amount. As an engineering feat, it's amazing, and I just think it captures wonderfully our abilities. And you know, there's another story at the same time while comets are in the news. Another neat thing that we've learned about comets is they're not just in our solar system. Recently, observations of a star, I think Beta Pictoris, 60 light years away, has actually been able to discern the presence of two large comet systems around the star. One, which is being tugged by a massive star, a massive planet, and the other looks like it was created recently by the collision of two planet-like objects. What's interesting is we have two populations of comets and asteroids in our solar system, one of which is largely affected by a massive planet, Jupiter, and one of which we may have come from the collision of two protoplanets that would have been planets if they hadn't collided. So we're already seeing something similar in another solar system. And that's rather fascinating, the fact that we can actually see clouds of comets around other stars. So we're learning about our solar system and potentially our origins and how typical we are or not typical of all solar systems in the galaxy.
With that information now, and with this landers on the comet, and everyone's kind of watching and seeing what happens, the comet is going to be nearing the sun, is it not?
Yeah.
What changes? What will we be watching for?
Well, the comet, as it nears the sun, begins to expel gas. And it would be great if, and when it gets near the sun, maybe the lander will have more sunlight and be able to operate. Eventually, of course, it gets close enough to the sun that the environment of the comet will become very volatile as it shoots things off, and the lander will stop operating. But the spacecraft is paralleling along beside it, so we'll be able to see the processes that basically produce the comet's tail, all the things that have been famous throughout human history. We'll get a close-up view of those very processes that happen as comets go around the sun and how they expel material, some of which later on remains in the solar system, because not all comets, some comets, of course, get absorbed in the sun. But like Halley's Comet, a lot of them have huge elliptical orbits that take them back every few hundred years. And so this process gets repeated thousands of times before the comet disappears, depositing material in the inner solar system. And
real quickly, the European Space Agency seems like it was taking the lead. Why them and not us? Where was NASA in all this?
Well, it had other priorities. I think it's, you've already heard me say, and I know I am not popular with some people to say that we spend too much time trying to send humans into space instead of doing the interesting stuff, like sending landers to see comets. And NASA has had several proposals, and we do have a planned rendezvous with a comet. But this was one of the European Space Agency's missions, and it started a decade ago. Remember, it started a
Yes.
lot more than a decade ago. It was launched a decade ago. The planning for it probably began 2 decades ago. And it's amazing that this thing took 10 years to get where it did. And so, and that means, by the way, that the technology on these spacecrafts are 20 years old.
Yeah.
And just think about that. I mean, you already know think about the technology on, say, Apollo. As you know, the computers on Apollo, they were far less powerful than the computers on my phone.
Yeah.
And yet we managed to send people to the moon. It's amazing.
Well, think about any computer 20 years ago compared to what you can get at...
Exactly. And these were, and Apollo was 50 years ago,
Yeah.
so it's amazing.
All right, let's keep it moving here. Now, the oldest living star in the universe has... How do we know this is the oldest living star?
It's got
in
a
the
really
universe?
long beard.
Now, this is a supernova. This is not exactly what
That's
we're
not a
talking
star.
about.
But supernovae are very important because they're exploding stars, and they produce the materials that produce you and me. As I've told you before, every atom inside you and me has been inside an exploding star. Because at the beginning of the universe, in the earliest moments of the Big Bang, the only elements that were created in those hot times when the universe was 1 billion degrees were hydrogen, helium, and a little bit of lithium. But all the important stuff, the carbon, nitrogen, oxygen, iron, all that stuff is created only in the nuclear furnaces inside of stars, which then are kind enough to explode and expel those ingredients, which then go into another generation of stars, which get cooked again and again and again. And the material in you and I have probably, and on Earth, has probably gone through 10 or 20 exploding stars. The most recent one probably 5 billion years ago, which triggered the formation of our solar system. Now, the oldest stars are there since we're building up heavy elements as material gets processed through stars, and they're essential for our existence. We couldn't have existed early in the history of the universe because there simply wasn't iron and oxygen and nitrogen and all the things we need, and carbon. So what we can look at is look at stars and look at the spectrum, the fingerprint of the light emitted by those stars, and it gives us the elements that are inside the star. And what was discovered by accident, and I'm kind of happy to say, as you probably know, I spend time in Australia, and I spend time at the Mount Stromlo Observatory. I have a part-time position there, and they have a star mapper which is looking at 1 million galaxies in the southern hemisphere. It also looks at stars, and it looked at the star, and it was suddenly weird because when it looked at its spectrum, there was no iron. There was less than 1 part in 1 million of iron compared to the amount in our sun. And if you work that out, that means that star must have formed right after the earliest generation of stars formed, a few 100 million years after the Big Bang. So it's estimated that formed maybe 200 million years after the Big Bang, 13.6 billion years ago, because it doesn't have any of the heavy elements that were later built up. And the big question is, how did it get there?
Well, and I was going to ask that because
Good, I was hoping you would.
in my research,
Yeah.
I discovered that the Milky Way is only 13.2 billion years old. So how come this thing's older than...
The Milky Way. Well, the point is the Milky Way didn't form all at once. The Milky Way formed up by cannibalism, if you wish. What happens is we think that the large galaxies don't form at once. What happens is small conglomerations of gas collapse, forming globular clusters and small satellite galaxies. They then collide and build up, and then as it gets bigger, just like Jupiter was eating comets, galaxies eat these small globs of gas and build up and build up and build up. So our Milky Way took time to build up because first these small things had to collapse. What is thought about this old star, it was probably formed and lived in a small gas cloud that existed before our Milky Way formed, and then it was captured into our Milky Way, which is why it's in our Milky Way.
All
now.
right. So that's how you get that difference.
That's how you get it forming before our Milky Way, then it gets eaten. And just like the food that you ate today was formed earlier, I assume.
Some of it a lot earlier.
Unless you eat it live.
Yeah, okay. All right, now, something else that I find this kind of stuff fascinating.
Good, I love your research.
This idea, I know, I do a lot of research on
I can
it.
see.
New coating material that radiates heat. Okay, we understand radiates heat back to the atmosphere. No, radiates heat beyond the atmosphere into space. How does this happen?
It's even better than that. I love this story because we're going to preview, spoiler alert, we're going to talk about climate change in a little bit. But this is kind of anti-climate change because climate change happens, and it's happening because sunlight comes and makes it through the atmosphere, and then gets converted into heat, which gets trapped in the atmosphere. The infrared radiation gets trapped in the atmosphere. These people have developed a material which does precisely the opposite. It reflects sunlight, so sunlight can't penetrate it. It just reflects it. It's a perfect mirror. But what it does is it takes the infrared radiation, the heat, and turns it into a frequency which does not get absorbed in our atmosphere and therefore gets emitted out into space. And space, of course, is cool enough, and that material basically doesn't even know our atmosphere is there. There are certain frequencies of radiation that don't get absorbed by radiation or atmosphere. That means all the heat light, the infrared light emitted by this material, does not get absorbed in the atmosphere. It does not heat up the Earth, therefore. And because it doesn't get absorbed in the atmosphere, it gets dumped into the vacuum of space. So it transports heat from in this case, an office building, directly out of the atmosphere. I mean, it would be fine if it transported it out of the building. It could help cool the building.
Sure.
But it would be bad for global warming because it would heat up the Earth. This thing is a material without any, it's basically a refrigerator that works without any power. It reflects sunlight, so the sunlight doesn't heat up the building. And it takes any heat produced by the occupants and the lighting inside the building and transports it directly into space because it emits it at a frequency of light that doesn't get absorbed in the atmosphere. So if you wish, it's anti-global warming, exactly. It's man-made. It's a man-made material, does exactly the opposite of what our atmosphere does.
And the key is transforming that heat into this infrared thing that can go straight through the atmosphere, like a little alleyway?
All heat, of course, gets emitted by, when you stand near your oven, you feel heat.
Yes.
That's infrared light that's coming from your oven. But most of the frequencies of infrared light that are emitted by the oven get absorbed by your body or the atmosphere. What they were smart enough to do was get a material that basically would absorb the infrared radiation from inside the building, the heat light, and turn it into a different frequency of infrared radiation that happens to be a frequency that can escape.
Okay, before we get, now let's get into global warming here in a second here, because we only got a few minutes left here, but that transformation process, doesn't that require energy? Doesn't that emit heat, if you will?
No, because materials do these things naturally. You emit, the clothes on your body take sunlight, absorb some of it, re-emit it, and sometimes produce different colors. It's just a property of materials when they absorb light. They don't always re-emit light in the same frequency they absorb it. So it's amazing. It's a wonderful, in this case, it's intelligent design, but intelligent design that really works.
Okay, well, we got that. You threw that in there. I caught that there.
Yeah, good. Thank you.
And so we got this now regarding a positive aspect of global warming and climate change. This as India decides it's going to go full bore into coal.
Yeah, the news on climate change has been miserable in the last year, and there have been really two things in the last month or two that, well, a whole bunch that are negative, and none of the news, except the United States just made a treaty with China, which in principle is nice. Except what happened is that India, which is burning 500 million tons of coal, has now said their goal for 2019 is to go up to 1 billion tons. Now, not only is that miserable, in fact, not only is that almost enough on its own to push us past the tipping point, which we're arbitrarily close to, which will ensure the Earth heats up to a level that is in many ways disastrous, we'll get to, but it's also awful for the environment there. It's strip mining. It's the worst polluting kind of coal mining, and it's really unfortunate that I mean, coal, you'll get letters for this, but coal shouldn't be, we should just forget coal. Coal is the worst kind of energy production. It doesn't even employ many people. But in India, it's the worst kind of coal production. And the fact that they're increasing over 5 years, 500 million tons a year of coal burning is disastrous at a time when, at the same time, we're getting news, well, we're already experiencing extreme weather. Some people say, well, look, it's the coldest winter, November and record. Where's global warming? But it's the extremes that happen when you inject more energy in the atmosphere because of global warming. You change things like this polar vortex and currents in the ocean. And we're seeing winter weather that's never been seen before, where people have to dig tunnels to get out of their houses in the East Coast. And these extremes of weather are another example of the injection of more energy in the atmosphere. And along with that, there was a recent report by the World Bank called Turning Up, I think it was called Turning Up the Heat or something. And what you see from the IPCC, the International Panel on Climate Change, their reports are extremely conservative because they have to get consensus. So they basically take the lowest common denominator. But climate scientists and the whole say the actual global warming is now much more likely in this century to be 7 degrees, not just 2 degrees. 7 degrees on average will just be extreme. In fact, there's good evidence that the West Antarctic ice sheet is already going to melt. And it's going to slide into the ocean. There's nothing we can do, even if we stop burning all fossil fuels right now. And if that happens, and it looks like it's inevitable, sea level rise will be 4 feet. So goodbye South Beach, Florida. Goodbye, in fact, for India, which is helping contribute to global warming, it's estimated that at least 37 million people will lose their habitat right now because of rising sea level. So it's an unfortunate situation. We're going to have to learn. In some sense, we can't stop it at the level that now exists. We hopefully will stop it at more extreme levels, which is what we need to do. But what already is happening is going to produce dramatic changes. And in some places in the world, there'll be no way of getting around it. We'll just lose Pacific Islands. But even in advanced places like the United States, there's going to be severe flooding and extreme weather that we have to get used to. And the point is, we broke it. We got to fix it. And we got to think, we can't just bemoan the future. We've got to think of ways to maybe try and capture carbon dioxide. We've talked about that.
All right. Well, we got to stop it right there. At least we got that one positive thing with the reflective mirror. So
yeah,
we got a good.
Let's end on a positive note. It shows that human beings, at least with technology, can try and address problems once we realize the problems are there and fund them. So, we've got to use our brains.
All right. I think we used our brains this show.
I hope so.
Good to have you here.
It's good to be here.
All right. And that is it for now. I'm Ted Simons. Thank you so much for joining us. You have a great evening.
Arizona Horizon is made possible by contributions from the Friends of 8, members of your Arizona PBS station. Thank you.